All right, now moving to the next chapter we're talking about now is joint probability distribution. So far we've focused on primarily on individual random variables and how we describe the distribution of individual random variables. On occasion, we've talked about collections of independent random variables, and in that case, we were able to study them in some sense jointly, like when we studied the minimum of a collection of exponentials. Now we're going to talk about a bit more of a complex topic, which is joint distributions. And the key difference here is it allows us to incorporate dependence among different random variables. So it's possible, for example, that two random variables vary in a way such that when one is large, the other is large, for example, or when one is large, the other is small. So an example would be if the random variable x and y, x was my height and y was my weight, or the height and weight of a person that you come across on the street. Well, any given person's height is going to follow some distribution. Any given person's weight will follow a distribution, but height and weight are not independent. People who are taller tend to weigh more. People who are shorter tend to weigh less. And so that would be an example of a joint distribution of two random variables that are not independent. So let's see how this works. So let's let B be a subset of two-dimensional space. Then two random variables x and y have a continuous joint distribution if there exists a non-negative function f such that the probability that the pair xy falls within the region B is now defined as a double integral over the region B of that joint density. No, it's the same concept, except now we have some two-dimensional curve that is assigning a density to every pair of points, and we're looking at the area still under that curve, but the area is now in two-dimensional space. Okay. And so if we write, so for example, if this is B, then we would integrate over that region. So that's what B is. And if we define an indicator, IB of XY, this is a 1 or a 0. 1 if the pair XY is in B and 0 otherwise. Then the double integral of B of the joint density can be written as an unlimited integral, so minus infinity to infinity on both x and y, of the function IB of xy f of xy dx dy. And this can be written as an integral so we write it as a double integral first with respect to X and then with respect to Y. But we can also reverse the order. And we can do first with respect to Y, first with respect to on Y on the inside, and with respect to Y on the outside. So this is how in practice we would calculate these probabilities. So the interpretation of this is that we suppose that the density, if we assume it's continuous at xy, then for B, defined as the rectangle with sides given by x to x plus dx, y to y plus dy. So it's the same concept, except now we're drawing a two-dimensional square with very small sides, right? So in this case, let's make this more regular, and let's call B this square going from x to x plus dx, y plus dy. Okay. Then the density we interpret as the probability that x is between x and x plus dx, y is between y plus dy divided by dx dy. Dx dy is the size of the rectangle. So it's the amount of probability mass per unit of area, right? Then f of xy is the joint density of x and y. So this is what's called a joint density. It behaves and it's used in much the same way as we think about densities in the continuous case for ordinary continuous random variables. But it is in two dimensions, and there are some aspects to it that are special and that need to be discussed in detail. Okay, so then there's a concept in when we talk about joint distributions, which is what's called the marginal distribution. So each random variable in and of itself is a random variable. So it has a density, which is irrespective of the other random variable being discussed. So this is a concept of what's called a marginal density or a marginal distribution. So suppose xy has joint density fxy. Then for a subset of R, so now we're thinking, okay, we have a subset of R, then how would we compute the probability that X is in a set? Okay, so let's think about what we're doing here. X and Y take values in two dimensions. And what we're doing is we're taking a subset of the real numbers, which we're going to draw as, let's say, this region here. So what does it mean for X? So if all we know is the joint variation of X and Y, then what has to happen in order for X to be in the set B? Well, what has to happen is, because we can't just talk about this line here assumes that X is in that region, but Y is equal to 0, which is only one of the many possible values of Y. So actually, we don't care what value Y takes, but we do care what value X takes. So anything in this region is going to be fair game, right? Because anything in this region gives us X in the set B that we care about, and Y is just any real number. So in terms of the joint distribution, this is the probability that the pair XY is in the product of B cross R. And so now we can write this as the integral of B. So going back up to here, integral over B. So we're integrating with respect to X on the outside, Y on the inside, R of F dy dx. Okay. This here is typically written then as fx of x because it integrates y out. This is called the marginal density. Why is this called the marginal density? Because if we use this notation, then we've expressed the probability that x falls in B as an integral of some function over the region B. That's exactly what we've defined a density to be. That's what a density is. And this is what that function is. It's the integral with respect to y, but it's still a function of x because we didn't integrate out y. Okay. So we say that x has marginal density given by the integral of the joint density over all values of y dy. We don't integrate out anything with respect to x. And similarly, y has a marginal density given by integrating the same function, the joint density, but now with respect to x. We get rid of x to get the density in terms of y. So what are some examples? So let's suppose that we define a joint density as cx squared for the region where x is less than y is less than 1 and 0 otherwise. Okay, so what do we have? Okay, what does this density look like? Well, it's cx squared and it's positive on the region from the unit square, but we need the unit square where x is strictly less than y. So it's only up here. Everywhere else it's 0. First question is to find C. This is over the region. over the entire region, we know that a density has to integrate to 1 because all of the probability mass goes to 1. So how do we do this? Well, if we choose to integrate by y on the outside, y can vary from 0 to 1. But then once we fix a value of y, what is x? X goes from 0 up to y. X cannot exceed y of cx squared dx dy. Okay. So this is integral from 0 to 1, c over 3, x cubed, y to 0, dy. So it's c over 3, y cubed, dy. So this is going to be c over 4, y to the 4th, c over 12, I'm sorry, c over 4 times 3, y to the 4th, 1 and 0. So then this tells us that c over 12 equals 1, and therefore c has to equal 12. And what's the marginal density of x? Marginal density of x is we have to integrate over all possible values of y for a given value of x. Well, once we fix x, we know that y has to be bigger than x. So it's integral from x to 1 of 12x squared dy. So this is an integral with respect to y. So 12x squared is a constant. Integral of x to 1 dy. So this is 12x squared 1 minus x. Marginal density of y. For a fixed value of y, we know that x can go from anywhere 0 up to y. It can't exceed y. 12x squared dx. So this is now an integral of 12x squared with respect to x. So that's going to be 12 over 3 x cubed from 0 to y, 4y cubed. So these are the densities, and these should add an indicator in to indicate clearly that these are only non-zero inside the unit interval. Otherwise, they are 0. Okay, so that's how we do calculations to get the marginal densities out of the joint density. We're going to have plenty of opportunities to work with joint distributions throughout the remainder of the course. And in fact, we're going to talk next about a special case of joint distribution where the random variables are independent. We're going to formally define independence of random variables for the first time.